Here we've been given the graph of f to the right, and that graph happens to be the derivative function of a function g. Part A asks, find any points of concavity on the function g. So taking a look at concavity, concavity is going to be the second derivative of g, or the first derivative of f. So we're talking about the slope on f. So what we want to look for is, where is the graph of f sloping up? So in this region here, from -4 to -2, the graph is sloping up. So the concavity is positive. Second derivative is positive, so the concavity is positive. The second derivative is undefined at -2, and where it's sloping down, the second derivative is negative. So sloping down, down, all the way down to +2. So between -2 and +2, although it changes direction, the slope is always negative. So we're going to have negative concavity in here, which means it's concave down. From +2 all the way to the endpoint 6, again, the first derivative of f is sloping up. That means the second derivative of g is positive. So we have, again, a positive concavity in that region all the way from 2 until the endpoint of 6. So in this case here, we could also determine that anytime it changes direction, we have an inflection point. So we have an inflection point here and here. So where it changes from going positive to negative, that would indicate inflection. In part B, it says find the critical points and determine if they're max min. So critical points are going to be where the graph crosses 0. Okay, so where that graph crosses 0 is going to indicate a horizontal tangent. So in this case, looks like we only have a horizontal tangent at x equals 1. And on the left side, we can see that it is above the x-axis. So this is all above the x-axis here, which means that it is a positive derivative, which means it is sloping up to that point. And then on the other side of that, we have all negative. These y coordinates are all negative, or the derivative is negative, means it is sloping down. So that indicates that that is a max. There's a max at x equals 1. This is a local max. Part C. Given that g of 0 equals -2, find the value of g at the critical points. So we can generalize y values of functions as the starting point, which we're going to call f of a. In this case, the starting point is going to be when x is 0, y is -2, plus the area underneath the derivative, or the displacement on the function. Okay, so it's going to be the area under the derivative. Okay, so we're going to find these y coordinates. Just going to put a box around that because that's very important. We're going to find the y coordinates. So we're going to find values of g, and we need values of g at the endpoints. So we need them, in this case, the endpoints are going to be -4 and +6, and we only have the one local max that we have to account for. So at x equals 1. So I want to find the g value at the endpoint to -4. To get there, I need to start at f of a. The starting point is going to be y equals 2. And then from there, we want the displacement from, in this case, it's going to be from 0, okay, all the way up to -4. Okay, and just want to highlight the fact that this a and this a are the same, right? Wherever the x coordinate a is, the f of a is the point, the y coordinate that we start at. So I have now, I want the area under, in this case, we've defined the graph of f. So I'm just going to write this as f of t dt. Okay, and I could write this as g prime. So the derivative, the area under the derivative. So the area under the derivative from 0 to -4, we just have to be careful because from 0 to -4, I'm integrating in this direction, which means this area that I'm going to find is above the x-axis is going to be a negative area. Okay, so when I find that area, I'm going to split it up into a trapezoid. It's going to be, the average height is 5 and the width is 2, so an area of 10. The triangular area to the left is going to be a width of 2, height of 6, so that this area is going to be 6. So the net area is -16. And it's negative because it's above the x-axis. So starting at 0, we went that way. So that's our displacement. So we're going to end up with, if this is equal to -2 plus that displacement of -16. Okay, just double checking that. That's -16. So the y coordinate works out to be, the g of -4 works out to be -18. Okay, so then we're going to do the same for 1. When g of 1 is going to be equal to our starting point of -2 plus the displacement from 0 to 1 under the derivative function. So the area under that derivative function from 0 to 1 is going to be this area in here. That area, it looks like it's a height of 4, width of 1. So 4 times 1 divided by 2. Now in this case, because we are integrating in the positive direction, that's going to be +2. So my coordinate is going to be equal to -2 plus the area of +2, and that gives me a y position of 0. Okay, so that's our local max. It's going to be at y equals 0. And then lastly, we want to calculate the g coordinate when x is 6. So again, we're going to start at -2. We're going to add the area underneath that graph from 0 to, in this case, we're going to go all the way to 6 under the derivative function. In this case is ft dt. So that area between from 0 to 6, well, that's +2. And then we also have this area all the way to 6. So that area is below the x-axis. It has a width of 5, height of 4. So 4 times 5 divided by 2 is going to give me an area of 10. And since it's below the x-axis, integrating from right to left, integrating from left to right, we have +2 minus 10. That's going to give us a net displacement of -8. So then this becomes -2 plus that displacement, which is -8. And so the y coordinate at x is 6 is going to be -10. So at the end point, that's -10. Okay, so the -4 happens to be the absolute minimum, and our local max at 1 is also our absolute maximum.